Classical Physics Tutoring Chapter 5 Section 1 Electric Field Equation. So we have the electron, the charge. The charge can be moved from conductor, because conductor's electron can be separated, to another conductor. Then it has an excess electron here, and electrons short compared with the number of positron. So it's charged, and this is a free electron. It's removed, and this free electron create the potential field. Now you know the Coulomb's law, just like a gravity law. The electron to electron, one must be opposite, attract each other, just like a gravity. And we don't use the Newton's law style, because here we use a field equation. And the field equation, we talk about Euler's method. Okay, so this generate the charge, generate the potential field at the location R. And you can imagine that there's a Q, and potential energy surrounding it will be like a spherical. Now the difference between gravity potential field is negative for m, so phi depend on m and the distance. Okay, but electron, positive electron, is going to create the repulsive against the positive electron, so it's going to be amount of Q and R. It's opposite, right? So what's happened is gravity is defined the slope of this potential field. So F was gradient phi R. For the electron, the F, which we called electric field, is going to be negative gradient phi R. The reason is, you look at the slope, it's a negative slope. So the negative value is going to tell us that field is this way, but actually field is going this way, so we put the negative to correct it. Now this is the definition of electric field, and the gravity force field is going to have a positive coefficient. That means the gravity is attracted this way, right? So there is a negative here. That's what this definition of electrical field is. So electrical field is defined by the gradient of potential field. Okay, then electrical field, like a gravity is actually F equals some gravity constant and R square, right? So we need a constant. So E is also has some constant, and amount of the charge R square. This R square, as long as you define this way, and potential field is 1 over R, this come out, and we show this to you. But here what we need to notice is we need some kind of constant, because we're going to define Coulomb's force by QE, and this is going to be the force, just like a gravity force is going to be M and gravity force, right? Okay, so same way, the gravity potential energy was the line integral of gradient, and potential field, the difference between the 2 points. And this is also same as the gravity field. The electric field we can define the same way. Okay, so this is a potential energy difference due to electric field. And now we define the flux. This flux is unique. We didn't have this kind in the gravity field, and this come out later. Flux is right now defined as epsilon E, and epsilon is not here epsilon 0. It's affected by the medium, the material the electric field goes through. Okay, so we know the equation. Divergent E is the surface integral. We take some surface, the enclosed 3D body, and the electric field going through this surface is same as divergent E, and that's going to be this going to be same as the charge volume integral. So we will have this equation. So according to this is purely mathematical result. According to this, just like gravity, the total amount, constant plus total amount of mass is going to be divergent force field. This is actually it's exactly same equation. Okay, now using this divergent and the gradient, we can get the equation divergent and negative gradient phi for the E is epsilon 0. We define this as a double derivative of phi, and this is the differential equation. So any potential field has to satisfy this differential equation. This is called Poisson's equation. And now this equation is called the Gaussian equation, and they carry the same meaning. We can use Gaussian's equation to solve some problem, but basically I think the charge create a potential field. What kind of potential field is the way it satisfies this differential equation. And if you see the potential field, you know there's a charge somewhere in the field, and the way this equation is satisfied, the charge is distributed in the field. Okay, and we have a boundary condition to solve this differential equation. So this is very basic equation for electrical field. So the Poisson's equation is the base for all the electric field, we can say. Well, you can bring up the Gaussian equation. Okay, so the Gauss law became the first equation of the Maxwell's basic 4 equation. The Gauss's law. But this Gauss law lead to the Poisson's equation, and Poisson's equation is used to solve the problem of charge versus potential field relationship. Okay, now we talk about the D. Why D is necessary. Okay, there is some material that generate additional charge. Suppose you have an electric field going, and this material calls dipole. The reason is this dielectric material, the electron and proton, is tightly coupled, but they are affected by electric field, so they cause a dipole. Okay, so dipole create a pair of charge, and this is not a true charge, not true charge, because it's not free charge, it's induced charge, and it's affect the potential field equation. And how it's affect? Well, divergent E plus divergent P over epsilon 0, we have this additional term equals rho over epsilon 0. Okay, so this P, how much P is induced? It's going to be epsilon equals epsilon 0, 1 plus chi E. This is the rate of induced dipole. Okay, so we use this to take care of the whole things, including the induced charge. So we can go back to equation divergent E equals the rho epsilon instead of epsilon 0 if we compound the effect of dipole. And this diagram kind of show how it's compounded. Okay, so in order to understand more here, I think the best way is to do some exercise, and I created several video for the exercise. Now we created Poisson's equation, and we said that's the basic differential equation to solve. So we know what kind of potential field is generated by the charge, and induced charge, it can be handled by the compound parameter, this. Okay, now this potential field, by taking gradient, we can get the electric field. So that's how it works. The relationship between charge and potential field is unique in a sense that there is only one solution exists in this differential equation. And this Poisson's equation is a second derivative, so we have to solve second derivatives differential equation. Now there is some mathematics manipulation to go through, and this takes a long time to explain, so I hope you check reference books or anything that help you to understand. It's integrated to be this shape. So basically potential field is going to be given by divergent E over R dV. So this volume integral is going to give this. Okay, so that's a kind of integral form of Poisson's equation. And how do you get E? The E equals epsilon delta and D, and D is related to true charge and plus induced charge. So instead of using E, if you use a D, you take care of this both, and using that you take integral, then you can get the solution. Now, the in the vacuum, there's no induced dipole, so it's simplified a little bit. Because if this is 0, then it's simplified. Now, if there is only induced charge, for example, there's an electric field and dipoles induced in the material, and potential field generated by this p vectors is going to be integral using Poisson's equation of p instead of e. Okay, or we can translate it into the surface charge, which is sigma n ds. Okay, so you have to go through some exercise program to understand fully about this implication of integral form of Poisson's equation. And this is the basic for the first section of the electric field. Okay, now the Coulomb's law is merely charge times E, and this already implicate that potential field is something to do with R1 coefficient, and if you take the derivative, E is going to be some kind of coefficient and the charge R square, and you multiply charge, so it's going to be this form. Okay, and this is the Coulomb's law, and the Coulomb's law is just a part of this Poisson's equation. It's come from the Poisson's equation, and this is the coefficient, coefficient for the force. Okay, so it's all integrated into the single theory Poisson's equation that is equivalent to Gauss' law, and that's can lead to the Coulomb's law. So it's all integrated, and that's why it's great. The Gauss law equation is adopted by Maxwell as the first equation for Maxwell's equation. Okay, so now since the charge and the potential field are related, and there is only unique solution for differential equation, what we do is, for the problem, like you have conductor, infinite conductor, and has a charge q, what kind of distribution on this conductor, the potential. This complex problem is converted into simpler problem. We treat this conductor as a mirror and assume there is a negative charge here on the other side at the equal distance. Okay, and if you solve this problem, then it satisfies the boundary condition. The argument is there are two maybe solution. The one is the original problem, infinite conductor with charge in front, and another solution is two opposite charge without any conductor. But if they satisfy exactly same boundary condition, then in fact they are equivalent. Okay, so that's what we do. Now, using this equation, which we know, when r equals r prime, then potential is 0, and surface charge is a derivative of phi along the x direction. So we can get the surface charge from here. Okay. Now we can expand this a little. Conductive sphere mirror. Suppose you have a conductor sphere and charge outside. What kind of charge distribution you get on this sphere? Well, in this case it's not straight conductor, but we assume same way that some kind of q prime existing at the distance a0 and work out the boundary condition, then we can make it work. That means this conductor is equivalent to having q prime at the distance a prime. It's equivalent, generate exactly same potential field. It's much easier to solve than this conductor surface charge distribution. Okay, and conductive sphere in the uniform electric field. Well, suppose you have a E, right? Potential field this. It's induce the charge on the surface. How much charge is going to be induced on the charge? This is same thing. So you have to go through this by yourself, because and also I created several videos that you can look for and practice this potential field versus charge. It's connected by Poisson's equation, and the Gauss law show up often too, and whichever you use is convenient. The point is this kind of conductor induce a lot of charge, and this is very complex problem and can be converted to the problem of having negative charge and positive charge here at the distance a, and potential field here is going to satisfy boundary condition for this. So from that potential phi we can get the surface charge. So that's the method that's sometimes used to solve the problem. Okay, so I hope you enjoyed this video, and next one we talk about magnetic field. Okay, so if you like, please subscribe.